utilizing the PCS MPR in numerical modeling for 8 years. He is also the senior R&D tribologist of PCS Instrument and also in the R&D team. And then for the USB high shear viscosity will be again under with Mr. Rory. And for the MTM EC and then the HPR rig will be again with Mr. Benjamin Wainwright. Okay, so let me introduce them to everyone. Okay, so this is PCS team. So may I call in number one, Mr. Tom? Can you wave your hand? Yes, that is Mr. Tom, and then Mr. Rory.
Hi.
Okay, great. So and then next is Mr. Benjamin.
Hi.
Okay, so all right, so I think we can officially open the event. So before we officially open, I will be calling our department head to do an opening remarks to officially run our presentation slides. May I call Kun Tadsalan, our department head for the petroleum division. Okay.
ก็สวัสดีขอบคุณสวัสดีแขกผู้ร่วมสัมมนาทุกท่านนะคะดิฉันทัศรันอัครีพันธ์เป็นตัวแทนฝ่ายบริหารของทางบริษัท Chemical House and Lab Instrument วันนี้ก็ขอบพระคุณทั้ง PCS แล้วก็ทางกลุ่มลูกค้าหรือว่ากลุ่มผู้เข้าร่วมสัมมนาของเราทุกท่านซึ่งถ้าหลายๆท่านเนี่ยได้คุ้นเคยกับทางบริษัทก็จะทราบว่าทาง Chemical House เองมีการจัดสัมมนาแบบเช่นอย่างนี้ไม่ว่าจะเป็นออนไซต์หรือว่าออนไลน์นะคะเป็นระยะซึ่งล่าสุดเราก็เมื่อจัดการทำไปเมื่อประมาณ3 เดือนที่แล้วนะคะหัวข้อแต่ละหัวข้อที่จะนำเข้ามาจะเป็นหัวข้อในเรื่องของเทคโนโลยีหรือว่าข้อมูลใหม่ๆข่าวสารใหม่ๆที่ทางเราจะเอามาแชร์โดยการร่วมมือกับทางโรงงานทางต่างประเทศครั้งนี้เราได้รับเกียรติจากทางบริษัท PCS Instrument นะคะซึ่งเป็นโรงงานผู้นำชั้นแนวหน้าในด้านถังไตรโบโลจีก็คือหัวข้อท็อปิกที่เราจะคุยกันวันนี้นะคะซึ่งเทคโนโลยีอันนี้จะสามารถช่วยดูในเรื่องของกายภาพที่เกิดขึ้นถ้าวัสดุเราได้มีการเสียดสีกันไม่ว่าจะเป็นทั้งเสียดสีหรือหล่อลื่นแล้วก็เสียดทานอันนี้ก็เลยได้ชื่อว่าเป็นไตรโบโลจีซึ่งหลายท่านในที่นี้น่าจะมีความรู้พอสมควรแล้วก็สามารถเอามาแชร์ร่วมกันได้นะคะระหว่างสัมมนาเพื่อเรามีเวลาไม่เยอะเพราะว่าวันนี้สปีกเกอร์เราค่อนข้างหลายคนนะคะวันนี้ก็เลยเดี๋ยวจะต้องรีบรวบรัดเวลานิดนึงจะเริ่มให้มิสเตอร์โรเบิร์ตซึ่งเป็น Product Manager Product and Application Manager ของทางบริษัท Chemical House นะคะและคุณวิภาวันที่เป็น Application Engineer จะช่วยกันสื่อแปลแล้วก็ดำเนินการสัมมนาของเราครั้งนี้อีกนิดนึงนะคะระหว่างสัมมนาให้ใครสงสัยหรืออยากมีคำถามอะไรเพิ่มสามารถพิมพ์เข้ามาในแชทบ็อกซ์หรือยกมือได้นะคะเพราะว่าทางเรามีทีมงานหลังบ้านที่คอยจะตอบแชทบ็อกซ์แล้วก็จบสัมมนาก็ขอเวลาอีกสักนิดนึงในการช่วยตอบคำถามหรือว่าสแกน QR code เพื่อให้ฟีดแบ็กกับทางบริษัทเรานิดนึงขอเปิดการสัมมนาครั้งนี้ค่ะขอบคุณมากค่ะ Thank you, Robert.
Thank you very much. Thank you very much to our department head, Kun Tadsalan. So we are now presenting to all of you the main topics of the webinar. Please note to all the attendees, thank you. And then for those who just recently come, that at the end of each topic, so there will be a summary translation by Kun Vipawan beside me. And we will be providing to the attendees, and you may open your questions or raise any you can interrupt at any time, or if you are comfortable more in putting your questions in the chat box, we have a team also to attend for that. And no further ado, now may we now roll the main topics and calling our PCS team, Mr. Will Hutchinson, to start in presenting the tribology fundamentals and lubricant properties. Okay, please come in, Mr. Will.
Yeah, hi. Hello, good afternoon, everyone. Welcome to the webinar. In this session, we're going to start by introducing you to our company, PCS Instruments, so you know who we are, before we sort of take you on a little journey into the sort of world of tribology. We'll introduce some of the key areas of tribology, and then talk about how these combine in a tribological system for both positive and negative results. We'll then go into the main body of the presentation, which will be done by my colleagues, that looks at our range of products and how they can help you solve sort of real world tribology issues in the field. Thank you. So just before we start, this is just our standard copyright notice. I'll just leave it up on screen for just a couple seconds, just so you can all sort of see. Let's start with, who are we? Who are PCS Instruments? We're a company that design and manufacture a range of laboratory instruments which are used for testing tribological properties of fuels and lubricants. This can be anything from diesel fuels to wind turbine gearbox oils, all the way to sort of things like chocolate and wine. It was formed as a company in 1987 by a team of research scientists who were studying in the tribology section at Imperial College London. It's remained in London ever since. We're in West London, growing and developing a range of industry-leading test equipment. To give you a sense of scale of the company, over those 35 years that we've been around, we've sold over 3,000 instruments into more than 100 countries around the world. We are PCS Instruments, the designs we create are also cited in over 500 peer-reviewed papers that address a wide range of applications and research areas. And that just highlights how integral our machines are to tribological research and development worldwide. In Thailand, in particular, our products are distributed by Chemical House and Lab Instrument Company, who are on hand to support our customers in the country. So, tribology, what is it? Tribology is the science and technology of interacting surfaces in relative motion, and that can be with or without a lubricant. The term was first coined in a paper called the Jost Report back in 1966, although the use of lubricants obviously predates that. It just wasn't called tribology. And you may ask, why is tribology so important? And that is because 1/3 of the world's energy is lost through friction in machines and other things, and optimizing your tribo system can help reduce that loss massively. Tribological systems are an immensely complex combination of different factors, but if we try to simplify a tribo system right down to its most basic thing, their behavior is dictated by the interaction between a contact and a lubricant. So, tribological contacts. There are many important aspects to consider when analysing a tribological contact. First up, we have the materials. In most mechanical systems, the materials involved are steels. However, this isn't always the case, and not all steels are the same. Differences between materials can significantly impact a tribo system, changing the pressures experienced by components, the damage that parts experience, so things like wear and fatigue, how additives in the lubricants affect behavior, and the surface features of the components. Like I said, not everything, not all contacts are steel. Different applications require different materials. For example, biocompatibility constraints are put on materials used in replacement body parts, like hip replacements. So now, next we have sort of large-scale geometries of contacts, and whether those are conformal or not. To simplify, conformal contacts, like you can see in the image on the screen, are ones where the surface sort of fits into each other. They have large contact areas, meaning they have lower contact pressures. This results in really small or smaller elastic deformations, and some typical places this sort of contact is found is in journal bearings, piston bushes, things like that. The non-conformal contacts, which are, you can also still see on the screen, are the opposite of conformal ones. They have much smaller contact areas, meaning they have much higher contact pressures. This results in larger elastic deformations at the surface, and some typical places you can find these are in roller bearings, gears, and cams. Next we have the roughness of the surfaces that are in contact. Even if something feels smooth to the touch, at a microscopic level, the surfaces will still be made of peaks and troughs, like valleys and mountains, yes. This roughness is a critical factor in the type and extent of damage a part will experience when in use. And as you can see from the examples on the screen, different roughnesses are deemed acceptable for different applications, as a balance has to be sort of measured between cost and then surface finish. Finally, just for this first bit, we have contact pressures. The contact pressures experienced in a tribo system will impact the amount of surface deformation seen on parts. The damage and failure mechanisms found in the system will also affect that. How the lubricants in the system behave, for example, are there additives activated when they're in the contact? The lifetime of the components, that's also very important. And as you can see below, there are some examples of the contact pressures seen in real-world applications. You can see that there is a big range, even within these sort of similar types of parts, depending on the specific use case. So I think we pause here for translation.
Okay, then thank you, Tom, for very much for that fundamentals of tribology part. So may I call our team in to translate in the local language?
ค่ะก็เนื่องจากว่าสัมมนาในครั้งนี้นะคะเป็นแบบ tribology webinar นะคะก็อันดับแรกเนี่ย tribology คืออะไรนะคะ tribology นะคะก็จะเป็นวิทยาศาสตร์แล้วก็เทคโนโลยีนะคะทางด้านพื้นผิวที่มีการคอนแทคกันนะคะทั้งสภาวะที่มีแล้วก็ไม่มีสารหล่อลื่นนะคะซึ่งในระบบเมคานิคอลต่างๆเนี่ยมักจะมีวัสดุที่หลากหลายนะคะทั้งที่เป็นโลหะนะคะเป็นพลาสติกหรือว่าวัสดุอื่นๆนะคะที่มีการผลิตขึ้นเฉพาะแต่ละชิ้นงานนะคะให้มีความเหมาะสมนะคะซึ่งความสัมพันธ์ของวัสดุประเภทต่างๆนี้นะคะกับการเคลื่อนที่นะคะอาจจะส่งผลต่อวัสดุที่ต่างกันด้วยนะคะทั้งในด้านของ friction นะคะหรือแรงเสียดทานนะคะหรือแวร์นะคะการสึกหรอของวัสดุนะคะแล้วก็ความสามารถในการหล่อลื่นนะคะซึ่งความสัมพันธ์เหล่านี้นะคะก็สามารถที่จะทำการศึกษานะคะได้โดยใช้เครื่องมือนะคะที่จำลองสภาวะการทดสอบนะคะเพื่อดูความสัมพันธ์ที่เกิดขึ้นนะคะ tribology contact นะคะแบ่งออกเป็น2ประเภทใหญ่ๆนะคะอย่างอันดับแรกเลยนะคะเป็นแบบ conformal นะคะซึ่งเป็นการสัมผัสแบบหน้าสัมผัสประสานกันนะคะซึ่งจะมีพื้นที่สัมผัสที่ใหญ่นะคะมี contact pressure หรือแรงกดทับที่ต่ำนะคะส่งผลให้มีการเปลี่ยนรูปแบบอิลาสติกนะคะเล็กน้อยนะคะโดยทั่วไปเนี่ยเราจะพบการสัมผัสลักษณะนี้นะคะอย่างเช่นใน journal bearing นะคะแล้วก็ piston bush นะคะที่อยู่ในเครื่องยนต์เครื่องจักรของเรานะคะส่วนอันดับที่2นะคะการสัมผัสเป็นแบบ non conformal นะคะเป็นการสัมผัสที่ผิวสัมผัสนะคะไม่ขนานกันนะคะแล้วก็มีพื้นที่สัมผัสเนี่ยที่สัมผัสกันน้อยนะคะลักษณะการสัมผัสประเภทนี้จะมี contact pressure ที่ ค่อนข้างจะมากกว่าแบบแรกนะคะซึ่งก็จะส่งผลให้มีการเปลี่ยนแปลงของรูปร่างนะคะที่มากกว่าแบบ conformal นะคะซึ่งยกตัวอย่างก็จะอยู่ในพวกroller bearing นะคะเกียร์นะคะแคมป์นะคะก็จะพบการสัมผัสประเภทนี้นะคะซึ่งนอกจากนี้นะคะในการ contact ของพื้นผิวนะคะยังขึ้นอยู่กับ roughness หรือความหยาบนะคะของพื้นผิวที่สัมผัสนั้นๆนะคะเพราะว่าบางครั้งเนี่ยวัสดุที่เราเห็นนะคะเราอาจจะมองเห็นว่ามันมีผิวเรียบนะคะแต่ในระดับที่ไมโครเลเวลแล้วนะคะเราจะเห็นว่าพื้นผิวที่เราเห็นนั้นนะคะอาจจะไม่ได้เรียบแบบที่ตาเราเห็นนะคะค่ะ
Okay, thank you. So maybe this time we will proceed to the lubricant topic.
Cool. So that was all sort of an introduction to tribology and contacts. So now we move on to the sort of other key part of tribology, which is lubricants. When we say a lubricant, when we talk about a lubricant, we mean anything that is within a sort of a tribo system which is there to reduce friction and to help parts move more easily. These can take many forms. Typical examples, like you can see on the screen, are oils, greases, surface coatings. They can also be solid or an emulsion. The formulation of lubricants is very important. It's probably the most important thing. One oil wouldn't work for every application. Different formulations will have very different properties and behave very differently in tribo systems. Some of these properties that will be different are the viscosity of the lubricant, the sort of degree of anti-wear protection it offers, whether it will form a surface film to protect against extreme pressures, and whether it will survive high shear events. Choosing and designing the right lubricant for the job can be the difference between efficient, long-lasting performance and premature failures in your tribo system and soaring costs. We see this all the time across a wide range of applications. So what does this all mean? Why is it important? These two main factors, the contact and the lubricant, will determine how your tribo system behaves. They will determine what lubrication regime is found. So are you seeing surface-surface interactions or a nicely lubricated contact? They will impact the amount of friction found. So is your lubricant causing increased friction or is it reducing it and improving efficiency? They will obviously also drive the thickness of your lubricant film in the contact. So are your surfaces separated, which prevents wear and reduces friction? Is your film too thick and reducing efficiency through churning losses? And finally, what damage will occur in the system and when? So will your design experience premature failures such as fatigue, wear, pitting or scuffing in the field? If everything works well, if you've sort of got the perfect lubricant for your tribo system, then you're in a great place. That normally means good lubricant films, low contact pressures, low temperatures. However, in practice, in the real world, you'll very rarely see a perfect system because there are always competing considerations and constraints such as manufacturing costs, which means you can't get exactly what you need. Often you see some issues, things like surface-surface or surface-to-surface contact resulting in wear, or high stresses and pressures resulting in fatigue, or high temperatures resulting in scuffing. This is where lab-based tribological studies come in and our machines come in. They let you evaluate exactly how your system will perform in the field, and from this you can optimize your design, the design of both your machines and your lubricants quickly, cheaply, reliably, all without having to resort to costly sort of full system, large scale tests. You can also precisely balance those competing considerations to find the best solution for you. So to summarize this intro portion of the presentation, tribology is critical in making sure moving surfaces do so in the most efficient and effective way possible. It allows you to understand the conditions the parts in your machine will experience when in use, evaluate how well they will work and how long they will last. Or if you're a lubricant producer, how well your product will help improve efficiency and the degree of increased protection it offers. Like I've said, it allows you to optimize your formulations to balance performance and costs, and possibly most importantly, it lets you do all that much more cheaply, quickly, and in a much more targeted way than with full-scale testing. Understanding the tribo systems found in your machines will save you time and money, all while improving your brand's reputation for providing top quality, long-lasting products. And I think we have another break.
Thank you, Tom.
ค่ะก็จากที่กล่าวมาข้างต้นนะคะการทำงานของระบบแมคานิคอลเกือบทุกระบบนะคะจึงจำเป็นที่จะต้องมีสารหล่อลื่นนะคะเพื่อที่จะลดแรงเสียดทานหรือลดการสึกหรอนะคะที่อาจจะเกิดขึ้นในระบบได้นะคะซึ่งสารหล่อลื่นเนี่ยก็จะมีหลากหลายรูปแบบแตกต่างกันไปนะคะอย่างเช่นออยล์นะคะกรีซนะคะsurface coating นะคะ solid lubricant แล้วก็อื่นๆอีกมากมายนะคะซึ่งในสารหล่อลื่นแบบต่างๆนี้นะคะก็จะถูกผลิตขึ้นนะคะให้มีคุณสมบัติที่เหมาะสมต่อการใช้งานในด้านที่แตกต่างกันไปเหมือนกันนะคะดังนั้นนะคะการศึกษาทางด้าน tribology นะคะก็มีความสำคัญนะคะเพื่อที่จะช่วยให้เราเนี่ยอธิบายได้ว่า lubricant นะคะที่เรานำมาใช้ประโยชน์นะคะมีประสิทธิภาพในการใช้งานเพียงใดนะคะระบบนะคะจะเกิดความเสียหายหรือมีอายุการใช้งานได้นานแค่ไหนนะคะซึ่งถ้าหากเราทราบหรือทำความเข้าใจสิ่งนี้ได้ก่อนนะคะก็จะสามารถออกแบบนะคะเพื่อป้องกันการเกิดความเสียหายที่อาจจะเกิดขึ้นได้นะคะเพื่อที่จะลดต้นทุนการผลิตนะคะประหยัดเวลาแล้วก็สามารถที่จะพัฒนาปรับปรุงโปรดักต์ของเรานะคะให้มีคุณภาพมากยิ่งขึ้นค่ะ
Okay, thank you for that, Will, and then to Vipoan. And then now we will move to the next topic, friction and wear properties, will be presented by Tom Wellham.
Final page just for me before I hand off to my colleague Tom. So where do PCS Instruments come into the equation? We manufacture a wide range of laboratory test equipment to perform those benchtop tests I was just talking about. All of our machines enable users to perform quick, easy to run, repeatable, reliable and accurate tests. They're also designed for versatility. So whether you want to run a standard test over and over to qualify an oil or do cutting edge bespoke tests designed with very specific applications in mind, our machines can meet your needs. They're used by industry and academia around the world to investigate a vast array of applications. And as you can see on the slide, this is our range of instruments. And I'll now hand off to my colleague Tom and the colleague, who will now go into much more detail about some of these instruments and how they're being used right now in the field to solve tribology problems. So, Tom.
Thank you. So I'm going to first talk about a general sort of purpose tribometer, desktop tribometer called the MTM, and also the MTM Slim. So the MTM is a very flexible benchtop tribometer. It has a ball-on-disc geometry. So it's designed for looking at measuring frictional properties in a wide range of tribological contacts. Many applications have been studied using the MTM, and we have a wide range of accessories to sort of broaden its use even further. For example, we have the option of soft specimens and a lower load option to allow us to look at biotribological contacts. And the MTM slim option, which is an optical system that allows us to measure tribofilm growth. And as well as things like we have a grease scoop and a grease applicator, which just allows us to make repeatable measurements of grease performance. We've got a huge number of materials and finishes of specimens, as well as different operating modes that we can measure friction under. And so I'll run through some of these accessories and some of the operating modes of the system now. Firstly, the capabilities of the rig. As I said, it's a ball on disc geometry. And one of the key features is that both of these are independently driven. So we can control the speed of the ball and the speed of the disc independently. This allows us to set the amount of sliding and rolling in the contact, which really gives us a huge versatility in the sort of conditions we can produce and the sort of contacts we can look at. So if you have a quick look at some of the elements of the spec, we can get up to 75 newtons on the MTM, which gives us a contact pressure of 1.25 GPa. And there we have specimens with slightly different geometries, which allow us to go to higher pressures still. And then speeds of up to 4 meters per second in entrainment speed. And then temperature-wise, we can go from ambient to 150 degrees. And we also offer an oil cooler, which circulates in journals beneath the pot that allows it to go even cooler than this. And another big advantage is a very small amount of lubricant, only 30 milliliters is needed for a test. So just some points about the relevance of the MTM to industry. It's used across lubricant and lubricant additive manufacturers to develop lubricants. And as we said, it's primarily used to measure the ability of a lubricant to control or reduce friction. Also, so as a screener test, it's small scale, and the cheap specimens compared to full scale testing means it can be used as a very good screener for more expensive full scale testing. And it's been shown that the MTM can correlate to these much more expensive tests. The slim system allows us to look at tribofilm formation and the growth of tribofilms, which helps us with the discovery of new additives and the design of new formulations. And also in standard testing, it's so easy to use. It's an automated system, so it's used widely to test every formulation to give a quick and simple comparison of the frictional properties. So the testing can take the form of different what we call step types. So we have Strybeck traction tests and time steps. So I'll go through these individually just to explain how each one works. Strybeck step is where we look at how entrainment speed affects traction or friction for a fixed slide roll ratio. So we change the speed and keep the slide roll ratio constant. A traction step where we fix the entrainment speed and then see how the slide roll ratio affects the traction. And then finally a time step where we look at the evolution of the traction coefficient over time, while we either ramp or keep the speed and slide roll ratio constant. So firstly, in more detail about the Strybeck curves, they can be really useful because by varying the entrainment speed, we can look at how the lubricant behaves in the different lubrication regimes. So at high speed, we're in the around here in the full EHD region. So this is where the oil itself is supporting the contact. So there's no contact, there's no metal to metal contact, and so it's the sort of base oil properties that are controlling the amount of friction in contact. As we move down through the speed range, we come into the mixed contact, the mixed regime, where we're starting to have some interaction between asperities in the contact. And right down at very low speeds, we're getting towards the boundary regime, where there's a sort of significant asperity contact, and the load is being supported a lot by actual metal to metal contact. And when we can test down in this region, we can look at how tribofilms form to protect the surfaces in these regimes. So traction curves, they're also very useful. we usually use the term traction to describe the use of frictional forces to transmit mechanical energy. So as mentioned in this type of step, we fix the entrainment speed, and then we vary the proportion of sliding to see how traction is impacted. So there's many benefits to looking at this, one of which is to look at the sort of the limiting shear stress of the lubricant. It's particularly useful in CVTs as well, where we're using the lubricant to transfer, with the aim of transferring a mechanical, transferring a force using the contact. So finally, the time step. This allows us to vary the speed and slide roll ratio over a fixed period of time. So it can be used independently, but often it's used in conjunction with other steps to allow for the development of tribo films and running in of surfaces. So we might want to impose a consistent level of sliding amongst when we're comparing multiple lubricants, for example, at an elevated temperature. So the nature, we have it when we run our tests, and this is common to all our instruments, we have a profile editor that allows us to customize each step that the machine will run, the durations, the conditions, which gives amazing flexibility to the sort of range of tests that the machine can run. And just as an example of how the sequences of steps work, so this is an example where we've run Stribeck steps in conjunction with periods of time steps. So we run a Stribeck. So this lower line here is our initial step where we do a Stribeck step. So we're looking at the friction compared to speed. Well, then in between this, we then do 5 minutes of running. Run another, then using a time step, then run another Stribeck step to get this one here. And we do this repeatedly. So after 2 hours, we keep doing periods of time steps and then Stribeck measurements, and we can see how the tribo film has evolved, changing the level of friction in the contact as the test has progressed. And we can combine this with the NTM Slim, which is the images here, which actually give us an indication of the thickness of that tribo film in the contact. And I think I'm going to pause here for some translation.
Thank you, Tom.
ก็สำหรับเครื่องมือทดสอบนะคะที่จำลองการศึกษาคุณสมบัติของการหล่อลื่นจากทาง PCS Instrument นะคะก็มีหลากหลายเครื่องทดสอบมากนะคะซึ่งเครื่องแรกนะคะที่นำเสนอในวันนี้นะคะก็คือ MTM นะคะซึ่ง MTM นะคะถูกออกแบบมาเพื่อวัดคุณสมบัตินะคะการหล่อลื่นนะคะของลูบิแคนนะคะที่ตัวเครื่องเนี่ยมีมอเตอร์นะคะ2ตัวนะคะที่สามารถที่จะควบคุมความเร็วของการหมุนนะคะของบอลแล้วก็ดิสก์นะคะที่สัมผัสกันได้นะคะนอกจากนี้ก็สามารถที่จะปรับพารามิเตอร์นะคะของการทดสอบได้หลากหลายเช่นเดียวกันนะคะตามที่เราต้องการศึกษานะคะก็ผลที่ได้นะคะจะทำให้เราเห็นถึงความสัมพันธ์ของการคอนแทคนะคะภายใต้สภาวะที่กำหนดของการทดสอบนะคะเพื่อที่จะสามารถอธิบายนะคะหรือดูประสิทธิภาพของการหล่อลื่นได้นะคะว่ามีประสิทธิภาพในการควบคุมลดแรงเสียดทานอย่างไรบ้างนะคะก็สำหรับเครื่องนี้นะคะก็สามารถที่จะช่วยในการทดสอบได้ประหยัดเวลาและลดค่าใช้จ่ายนะคะเมื่อเทียบกับการทดสอบที่สเกลใหญ่ๆนะคะซึ่งก็จะเหมาะกับงาน R&D นะคะที่ช่วยในการพัฒนาproduct นะคะของ lubricant แล้วก็ additive ได้ค่ะ
Thank you for that translation. So maybe we proceed to continue to the presentation from PCS.
Yes.
Okay.
Okay, thank you. So we're going to look now at a few applications of the NTM, not just in the standard steps, but some of the alternate accessories that can be used with the instrument. So firstly, an interesting application is to test seal material. So seal testing is traditionally sort of split into two categories. So simple wear testing, such as using a pin on disc, or testing the complete seal in place. So the first method, a pin on disc, often bears very little relevance to actually the final application. And the second is generally a very expensive test and is actually quite unsuitable for developing new materials. So we have this accessory, an O-ring holder for the NTM, which allows the NTM to be used to evaluate the performance of seal materials under a variety of conditions. So we have so we can have a look at here, for example, of a seal in place in the system. The seal replaces the ball specimen and then runs against the disc here. And as I said before, we can impart a fixed amount of sliding in the contact. So here we've chosen 50% slide roll ratio. This also uses the low load beam for the NTM, which takes the load range much lower and allows us to test this at 3 newtons to reduce the contact pressures further to a more realistic contact pressure for this system. And here we're looking at, in the 2 results, the difference between using a smooth disc and a rough disc. These are also things that we supply. We supply NTM specimens in a variety of materials and also surface finishes, so different roughnesses. And you can just see here the impact of the roughness, not so much in the at the higher speeds where we're in EHD or the hydrodynamic regime, but as we get more down into the lower speeds, moving into the boundary regime, the difference that the rough disc makes on the friction of that seal. So biotribology is another interesting application for the NTM. It's an expanding field of research. NTM has an excellent track record of giving very useful, repeatable friction measurements in soft contacts, a bit like we've just shown. We can use a variety of materials for looking at biotribological studies, but the use of PDMS for either one or both of the surfaces is very common in the literature. So we can adapt the NTM, as I mentioned, using the low load beam, which brings us to a load range of 2 to 8 newtons. And we can use it to look at artificial joints, mouthfeel, cosmetics, amongst many other, pretty much any biological contact you can think of. An example of some of the work we've seen here, where there's a comparison's been done of full fat and fat-free yogurts, so with and without artificial saliva. And there's a clear difference here between the sort of lower friction here of the full fat yogurt here shown in green, as compared to the fat-free yogurt in red. It's also quite interesting to note how the influence of saliva is much greater in the full fat yogurt. So if we look, the fat-free yogurt with saliva is blue here, and the full fat yogurt with saliva is green here. So the saliva is having much more of an impact on the full fat yogurt than it did on the fat-free yogurt here, particularly at these sort of low speeds. So in the paper we've cited just here, the authors were able to see a very good agreement between the NTM's tribological measurements and the results of a panel test, which sort of demonstrates the power of such tools to look at low-fat dairy replacements and dairy-free replacements in food. One final application is looking at, away from biotribology now, looking at some work that was done on wheel rail friction using the NTM and the grease scoop and applicator accessories. So in the rail industry, top of rail products and flange products are used to control the friction between the rail and the wheel. With the top of rail product, we're looking at reducing the amount of friction over just the dry contact, but we don't want to just use a grease. We want significantly more friction than that to allow us to accelerate, keep on the track nicely. So the NTM was used as a study in this. There's a phenomenon in trains which you can hear when you hear the screeching as trains go around corners or when braking, and that's this sort of a stick slip system that I've kind of tried to illustrate here. If this is they use the term creepage, which is the same as slide roll ratio, but if we have a certain amount of sliding, we have this unstable system where we come over this hump and we keep oscillating between different levels of sliding in the contact, and that oscillation is the screeching that you can hear. So the use of friction modifiers in these top of rail products allow us to have what we call positive friction characteristics. So as sliding increases, the traction coefficient increases. So we have this sort of behaviour, which means we never get into this unstable oscillation. So there was a study into this using the MTM, and it was found to very well be able to differentiate between these different top-of-rail products. End up being cited in EN 15427 as an indicative test. So as we can see here, there's some now qualifications on the level of traction that we see in the MTM to allow these products to be used. I think I'm pausing here.
Okay, sorry, thank you, Tom ค่ะก็สำหรับ MTM application นะคะก็จากที่ทอมนะคะได้พรีเซนต์ไปเมื่อสักครู่นะคะนอกจากจะทดสอบ lubricant ได้แล้วนะคะยังสามารถที่จะนำไปใช้ทดสอบกับแอปพลิเคชันอื่นๆได้ด้วยนะคะอย่างเช่นอันแรกนะคะสามารถที่จะนำ MTM นะคะไปทดสอบกับproduct ที่เป็น seal material นะคะอย่างเช่นการทดสอบ O-ring นะคะซึ่งสามารถที่จะนำ O-ring นะคะตามสไลด์ก่อนหน้าเนาะมายึดกับตัว specimen นะคะเพื่อทดสอบประสิทธิภาพของวัสดุ seal นะคะภายใต้ condition ต่างๆนะคะที่สามารถที่จะออกแบบนะคะกำหนดได้เองนะคะในสภาวะที่จะใช้งานนะคะหรือ2นะคะสามารถนำแอปพลิเคชันนี้นะคะไปทดสอบทางด้านtribology นะคะซึ่งก็จะใช้ศึกษาวิจัยทางด้านผิวสัมผัสทางด้านชีวภาพนะคะอย่างเช่นครีมบำรุงโลชั่นนะคะกระดูกอ่อนข้อต่อนะคะหรือว่าจะเป็นความรู้สึกทางด้านในปากนะคะอย่างเช่นโยเกิร์ตนะคะโยเกิร์ตที่มีการเติมไขมันแล้วก็ไม่มีการเติมไขมันนะคะหรือfree fat นะคะก็จะส่งผลให้ความรู้สึกในปากตอนที่เรากินโยเกิร์ตนะคะให้ความรู้สึกที่แตกต่างกันนะคะว่าแบบสมูทหรือเปล่านะคะก็อันนี้ก็สามารถที่จะนำแอปพลิเคชันนี้นะคะไปใช้ได้เหมือนกันนะคะแล้วก็อีกอย่างหนึ่งนะคะในการที่จะออกแบบระบบล้อและรางของรถไฟฟ้านะคะก็สามารถที่จะนำไปใช้ประโยชน์ในการศึกษาทางด้านการเสียดทานของล้อและรางนะคะเพื่อที่จะให้มีประสิทธิภาพในการใช้งานที่ดีขึ้นนะคะลดเสียงนะคะลดแรงเสียดทานที่เกิดขึ้นนะคะที่อาจจะเกิดการกระตุกนะคะในระหว่างที่รถไฟฟ้ากำลังที่จะเบรกนะคะก็ช่วยตรงนี้นะคะเพื่อให้การเบรกที่สมูทขึ้นนะคะค่ะก็ถ้าเกิดว่าลูกค้าท่านใดนะคะมีคำถามนะคะสามารถที่จะยกมือนะคะเพื่อที่จะ request ที่จะเปิดไมค์ถามได้นะคะหรือว่าสามารถที่จะพิมพ์คำถามมาในแชทบ็อกซ์ก็ได้นะคะ
Okay. Thank you. Back at you, Tom.
Thank you. So yeah, I'm just going to talk now about the one of the NTM's most widely used accessories, the Slim system, also known as the 3D mapper or the 3D mapper. So it uses it's an optical interferometer which allows the thickness of tribofilms to be measured while the specimen is mounted inside the MTM. So it's got many uses, and so I'll explain a few of these now. So the system works by bouncing a white light off a semi-reflective disc. Part of the light is reflected directly back. Part of it goes through the contact reflects off the steel ball, and when the light recombines, we have constructive interference at different frequencies depending on the thickness of the anti-wear film that's formed on the surface. So the way it works in the MTM, when we're running a test, the ball is rubbed against the metal disc. As I said, using a time step that allows us to build up the tribofilm. And then we backload the ball against this glass window that sits above the lid of the MTM. And this is with the ball stationary. And then we take a picture using an attached camera, and that allows us to, we can translate the image into a measure of film thickness or tribofilm thickness. So this is a typical use case showing how tribofilms evolve in different oils. So we took a series of timed steps represented here by sliding distance. So we set a speed and set a duration, and from that we could work out the distance that we wanted. This compares 4 different oils, and on the y-axis here we have film thickness in nanometers. It shows how varied tribofilm formation can be between different chemistries. We have some some fluids that form very little or no film, and then we can see how some take slightly longer to start building up the film thickness, and others that form earlier and actually are slightly unstable. So there's a bit that's sort of worn away as the sort of test progresses. And as well as the average film measurement, which I'm showing here, which is an average of an area of the contact, we can also use the provided software to give us a full map of friction across the entire contact. So just in a bit more detail, here's 3 oils looking at how the tribofilms have developed, and this just gives an example of what the images look like and the sort of insights we can get into the tribofilm using the NTM Slim. So we start off here with nice clean surfaces for all 3 tests, and as we progress we see the very different development of these tribofilms. So this one we developed quite a small, quite a thin film. Here we've got a very sort of homogeneous, smooth tribofilm across the whole part of the contact, whereas here we can see how rough and much thicker that tribofilm is, varying as we go across the contact. And these details that are shown in these images, they give chemists and oil formulators great insight into developing new oils. I'm going to go through this very quickly. I'm going to skip quite a lot of this because I'm conscious of time, but it just it illustrates here how tribofilm formation really can affect the level of friction in the contact. Starting here with 2 different tests. This is our baseline Stribex step, showing how friction varies with speed. We then do a long period here of running, so 120 minutes of running in using a time step. We're measuring friction throughout this, and we can see how the friction changes differently between the oil here on top and the oil here on the bottom. And then when we take another Stribex step at the end of the test, and we look at the difference, and we also take a slim image at the end of the test, just seeing how different now that behaviour, the friction in the contact is. So just finally about the NTM, why is it so useful? And I hope I've demonstrated that the Slim can be very useful in developing new anti-wear and other boundary film additives, as well as being useful in perfecting formulations that develop a stable tribofilm, so sort of helping to control friction and wear. With the Slim, the NTM can also be used as a screener for new additives and formulations, which can save significant costs compared to large-scale testing. And finally, with increasing restrictions on traditional anti-wear additives such as NTDP, the NTM Slim is a great tool to look at and compare entirely new additive technologies. So I'm going to pause here again.
Okay, thank you ค่ะก็สำหรับสลิมนะคะเป็น optional 1นะคะที่ต่อกับ 3D camera นะคะที่จะสามารถให้เราเนี่ยดู thickness ของ tribofilm ที่เกิดขึ้นได้นะคะแล้วก็ดูการเปลี่ยนแปลงนะคะของ tribofilm ที่เกิดขึ้นในระหว่างที่ทำการทดสอบนะคะลูกค้านะคะสามารถที่จะถ่ายภาพฟิล์มนะคะที่เกิดขึ้นนะคะในโปรแกรมซอฟต์แวร์เนาะเพื่อดูลักษณะของการเกิดฟิล์มนะคะโดยการทดสอบนี้นะคะเหมาะสำหรับผู้ที่ผลิตลูบิแคนต์นะคะที่มีการเติมแอดดิทีฟนะคะชนิดแบบแอนตี้แวร์นะคะที่ป้องกันการสึกหรอนะคะแล้วก็สามารถที่จะศึกษาลักษณะของฟิล์มที่เกิดขึ้นนะคะเมื่อใช้งานได้ค่ะค่ะ thank you please continue
Thank you. So next, closely related to the NTM is another instrument called the ETM. So the ETM is very similar in terms, well, it's identical in terms of geometry, ball on disc, specimens of the same size. The main difference is that we can now go up to loads of 1650 newtons. It also has the slim option to look at tribofilm growth, but now under these sort of more extreme contact pressures. So here are some of the specifications for the ETM, and just sort of comparing here the sort of contact pressures that we're able to achieve. So up to 3.5 gigapascals with the same geometry specimens as with the NTM. And this sort of shows the contact pressure range we're able to test under. Otherwise, the spec is very similar. So a little bit more about contact pressures with the standard specimens, as I say, up to 3.5 gigapascals. But we can actually we can use tungsten carbide specimens if we want to go even higher. Contact pressures as much as 7.1 gigapascals, so extremely high. Or if we want to stick with steel, we can change the geometry of the ball to give a sharper radius, which increases contact pressure, and that will take us up to 4.4 gigapascals, still with a steel contact. So the high contact pressures possible on the ETM, they allow us to mimic the conditions seen in very highly loaded gears and bearings, which helps with the development of new lubricants, coatings, and materials. So I'm going to mention a few applications today, such as the ability to generate high load traction curves to investigate the sort of mechano-tribofilm formation, and also to evaluate the scuffing resistance of lubricants under these very high contact pressures. Just as an example of the scuffing here, we can see the sort of range that the ETM gives us in terms of contact pressures and speed when we're looking at scuffing as compared to the NTM. So traction curves, they're made in the same way on the ETM as the NTM. And the graphs here on the left just show 4 traction curves at different contact pressures from 1 to 4 gigapascals. This is from a paper from here in Tribology Letters. So we can see the initial slope of the curves increases significantly as we increase contact pressure, and we also arrive at a much higher traction coefficient at significantly lower slide roll ratios as we'd expect. And the rapid rise in the traction coefficient at low slide roll ratios in these high pressure charts here is very significant. Rolling element bearings, they don't operate in pure rolling. Typically for deep groove ball bearings, for example, we have a small amount of sliding, typically between 1 or 2% slide roll over much of the ball and raceway contact. And this can be higher in other rolling bearings. So to understand, in bearings we are looking at pressures, contact pressures around this sort of magnitude. So the importance of this region and understanding how friction is affected by lubricant formulation is very important. We also see some other interesting things from this graph. We see the leveling off of the traction curve due to shear thinning, and at very high slide roll ratios and very high contact pressures, we also see the reduction of the traction coefficient starting here due to shear heating. It's heating inside the contact. So from a mechanochemistry side, this was a paper. This comes from a paper published in 2020, and just very quickly, it shows how previously it was thought that the development of ZDDP films required a sort of metal-to-metal contact, but actually using the ETM in this paper, it was shown that it's actually, rather than being hydrostatic pressure that's responsible for tribofilm growth, it's actually shear stress dependent, so we can have a full film, but if the shear stress is high enough, we can still develop ZDDP films. And we see this shown here, so these top 2 here, much higher friction coefficients, and using the ETM slim, we see the development of tribofilms, whereas here, where the friction is significantly lower, Otherwise, identical conditions, we see much less of a tribofilm. Another example, as mentioned, was scuffing, looking at scuffing. So it can be using a time step on the ETM, we can ramp load, sliding speed, and entrainment speed to increase the severity of the conditions seen in the contact. So this shows 3 different oils, and over time we're ramping these parameters as shown here, and we can see with very good repeatability the point at which scuffing occurs, and how that can be picked out between these different oils. So again, why is the ETM useful? It's used to study the effects of high contact pressures on the performance of lubricants, which are relevant to some advanced gear and bearing applications. We can see, well, we have seen that the chemical additives can behave very differently in the contact, which is not yet fully understood. So the ETM can be used to help study these. And as a screener for example, the FZG scuffing test, ETM specimens, the test is much quicker, the specimens are much cheaper, and so it's a great way to sort of screen lubricants for that test. And as it says here, it's a unique instrument with no alternative. So I'm going to hand back to the translation.
ก็สำหรับ ETM นะคะก็เป็นเครื่องทดสอบหนึ่งนะคะที่คล้ายกับ MTM นะคะแต่ว่าตัว ETM นะคะสามารถที่จะเพิ่มน้ำหนักโหลดนะคะได้สูงสุดถึง 1,650 นิวตันนะคะในการทดสอบนะคะเพื่อศึกษาผลกระทบนะคะของ High Contact Pressure นะคะที่มีต่อประสิทธิภาพของสารหล่อลื่นนะคะที่เกี่ยวข้องกับการใช้งานอย่างเช่นในเกียร์นะคะใน bearing บางประเภทนะคะซึ่งภายใต้ High Contact Pressure นะคะ Additive ในสารหล่อลื่นแต่ละชนิดนะคะก็จะทำงานแตกต่างกันออกไปนะคะซึ่งสามารถที่จะใช้ ETM นะคะเพื่อศึกษาผลกระทบนั้นได้นะคะเพื่อให้เราสามารถที่จะdevelop นะคะ additive ชนิดใหม่ๆนะคะให้มีประสิทธิภาพนะคะนอกจากนี้นะคะยังสามารถที่จะทดสอบหาscuffing performance นะคะของสารหล่อลื่นได้เช่นเดียวกันค่ะ
Okay, thank you for that. So I think we will be moving to the new topic, which is the elasto-hydrodynamic lubricating regime. So moving from traction or friction measurement by the MTM, let's continue the presentation to the topic to measure the thin film that is formed during the EHD. So using this EHD rig. May I call now Mr. Rory to proceed with this presentation.
Yeah, thank you, Robert. Yes, that's right. I'll be talking about the EHD rig, which is PCS's instrument for measuring the thickness of lubricant films. This machine allows accurate measurement of film thickness under conditions close to those of real machinery. It's applicable to base oils, new lubricant formulations, as well as polymer additives like viscosity modifiers. It's also commonly used in research, analyzing the fundamental aspects of EHD lubrication. So what it's actually doing is, as shown in this diagram here, we're using a microscope to look through a glass disc at the contact between the steel ball and the glass disc as they roll together. And now running through the capabilities of the EHD rig quickly. It can measure lubricant films up to 1,000 nanometers or 1 micron, and that can be under contact pressures that range from roughly 0.2 to 2 gigapascals, depending on the contact conditions, and that can be at entrainment speeds of up to 4 meters per second. And like the MTM, an advantage of this machine is that the sample volume required is actually quite small. In this case, 120 milliliters. So there are 3 fundamental techniques that the machine is capable of performing. There's film thickness measurement, which is fundamentally very similar to the process that Tom described earlier, except in this case we're taking a very accurate measurement, accurate to theoretically 1 nanometer or so, across the center of the contact. It's also capable of contact mapping with the SLIM method, which is exactly like what Tom described. The difference here is that we're looking at the rolling contact, and we're measuring the actual thickness of the lubricant film separating the surfaces. It can also separately perform traction testing, and the advantage here is that you can measure film thickness and then traction under very, very similar test conditions. So the rig mimics the contact conditions of applications like bearings and gears, allowing evaluation of oil formulations and important mechanisms like lubricant starvation. And that gives very useful information to lubricant engineers relating to real applications. And actually, film thickness is specified in some lubricant specifications. For example, the Dexron 6 specification by General Motors for automatic transmission fluids actually specifies the minimum film thickness allowable under certain conditions. So two applications that I'll mention here are bearings, in which the contact conditions like speed, temperature, and other conditions can be replicated, and so a film thickness estimate can be achieved using the EHD. So that would indicate whether the lubricant viscosity is sufficient for your bearing application. Greases are another area where understanding film thickness behavior allows optimization of performance. So here you can see that the grease, which is the two lines up here, shows much thicker films at low speed when compared to the base oils. And this effect is dependent on the size of the thickener fibers, which is something that can be controlled in manufacture. Next, I'll talk about the spacer layer image mapping, as was introduced earlier, but in this case, it's in the context of the rolling contact. So the contact itself is imaged, producing these colorful images here. The color of each specific pixel in that image can then be transformed into a film thickness value using a calibration curves. In that way, the whole surface of the contact can be mapped. And this allows the study of surface topologies. So these are some images from research into different types of roughness, as well as the behavior under starved conditions. So in this image, you can see that I hope you can see the inlet meniscus of the lubricant here is actually approaching the contact, and as a result, we've had a collapse of film thickness. So this region has very thin films, while this region has much thicker films, and that behavior is a result of starvation. So this can be studied using the SLIM technique. An important ability of the EHD rig is to evaluate the pressure viscosity coefficient of a lubricant. So viscosity increases exponentially with pressure. In this case, for an oil at 20 degrees Celsius, the viscosity increases more than 1 million times when going from atmospheric pressure here to approximately the pressures of a tribological contact. And that effect is actually really advantageous because it allows surfaces to be separated by extremely small contacts. But it needs to be very well understood in order to produce effective lubricants. Current trends are towards base oils with a reduced thickening effect with pressure. And if this isn't well understood, that could lead to high friction and wear. This effect can be described with a single parameter called the pressure viscosity coefficient, or alpha value. And using PCS's alpha value application, the film thickness results from a test can be fitted to a model for film thickness, providing a simple method to obtain a lubricant's pressure viscosity coefficient. So to summarize the EHD rig's capabilities, it can measure the film thickness of lubricants under EHD conditions, either with the extremely accurate interferometry technique or the slim contact mapping. That can allow optimization of lubricant viscosity, allowing maximum efficiency while still protecting surfaces from wear. The EHD is commonly used to evaluate film thickness behavior of new lubricant formulations, base oil mixtures, and viscosity modifiers, as well as being able to evaluate the pressure viscosity coefficient of lubricants. It's also used in research, analyzing the fundamental mechanisms of EHD lubrication. And I think at this point, I'll pause for translation.
Thank you, Rory.
ค่ะ ก็ในสภาวะที่มีการหล่อลื่นแบบอิลาสโตไฮโดรไดนามิกนะคะ หรือที่เรียกสั้นๆว่า EHD นะคะ สามารถที่จะวัดประสิทธิภาพของลูบิแคนนะคะ โดยใช้ EHD ได้นะคะเพื่อช่วยวัดฟิล์มthicknessนะคะภายใต้คอนดิชันการทดสอบนะคะที่จำลองสภาวะนะคะของการทดสอบใกล้เคียงกับการทำงานจริงนะคะโดยวัดความหนาของฟิล์มนะคะได้ถึง 1,000 นาโนเมตรนะคะแล้วก็สามารถที่จะแสดงผลความหนาของฟิล์มนะคะในระหว่างที่ทำการทดสอบนะคะแล้วก็นอกจากนี้นะคะยังสามารถที่จะถ่ายภาพลักษณะของการเกิดฟิล์มบนพื้นผิวได้นะคะโดยใช้สลิมได้นะคะอย่างเช่นคล้ายกับก่อนหน้าเลยนะคะซึ่งสำหรับ EHD นะคะสามารถที่จะวัดค่าสัมประสิทธิ์ความหนืดได้ด้วยนะคะที่ high pressure นะคะซึ่งเหมาะสำหรับผู้ที่ผลิตลูบิแคนนะคะเพื่อที่จะพัฒนา product หรือกำหนดสูตรลูบิแคนนะคะให้ดีขึ้นนะคะซึ่งทาง PCS นะคะมี alpha value application นะคะที่สามารถที่จะประมาณค่า pressure viscosity coefficient แบบอัตโนมัติได้ด้วยนะคะซึ่งก็เหมาะเป็นอย่างยิ่งนะคะสำหรับผู้ที่ผลิตpetrochemical lubricant นะคะที่ต้องการรักษาสภาวะในการสัมผัสกันของสารหล่อลื่นนะคะเมื่อนำไปใช้งานค่ะ
Okay, so we may now proceed to the high-speed EHD version.
Okay. So recently we launched a higher speed version of the EHD rig. So I'll talk briefly about the benefits that this brings. At high speeds, various effects such as starvation and shear heating occur, and that can cause film thickness to deviate from expected behavior. Typically, that means film thicknesses are lower than expected, and that can definitely be detrimental to efficiency and life of the component. One application that often operates at very high speeds is the drivetrain of EVs. Using the EHD high speed, these conditions can be replicated, and so the lubricant's the lubricant's response to starvation and other effects can be assessed. Another example where high-speed behavior is different to lower speeds is that of emulsion lubrications. So this is another example where the high-speed EHD can help you understand more about that application. In that specific case, the effective viscosity of emulsions can greatly reduce under high speed conditions, close to that of water. So I wanted to cover why we think it's important to test at high speeds. So here's shown some work from researchers at Imperial College. And this plot on the right shows that, which was taken using the EHD HS, shows that the EHD films, the measured films, are actually significantly thinner than the standard model for film thickness predicts. And it was shown in this work that this behavior was caused by a combination of inlet shear heating, which reduces viscosity, and inlet starvation, which I showed earlier can greatly reduce film thickness. It's difficult to predict these effects without actually measuring them. So the EHD HS is very useful for directly measuring how these effects occur. So the researchers found that shear heating effects varied significantly on the type of base oil, and therefore different correction factors were required for the different oils, which had to be based on experimental results. So it's difficult to model this type of behavior, but the EHD-HS allows measurement and assessment of the behavior of different oils under these effects. So much like the standard EHD, the EHD-HS can deliver a wide range of contact conditions in terms of temperature and contact pressure. But while the standard EHD can go up to a maximum entrainment speed of 4 meters per second, the EHD-HS can reach 20 meters per second. So that makes it applicable to applications such as electric vehicle drivetrains, additive formulation in automotive lubricants, metalworking fluids and emulsions, high-speed turbine oils, as well as greases, which are particularly vulnerable to inlet starvation. So to summarize this quick introduction to the EHD-HS, this machine is the high-speed upgrade to the standard EHD and is similar in capabilities except that it can reach up to 20 meters per second rolling speed. This makes it suitable for the film thickness measurement of lubricants for high-speed applications like electric vehicles, which are trending to smaller and faster conditions, as well as a range of other options. So in addition to the ones I've already mentioned, things like motorsport, elevators in tall buildings which travel extremely fast, machine tool spindles, and aviation gearboxes. Finally, it's useful in the research of fundamental effects like inlet starvation and shear heating, which can have significant impact at high speed.
ค่ะก็สำหรับ EHD High Speed นะคะเช่นเดียวกันนะคะก็เช่นเดียวกันกับ EHD นะคะแต่ว่าในส่วนของ EHD High Speed นะคะจะช่วยในการทดสอบนะคะเพื่อศึกษาฟิล์ม thickness นะคะของ lubricant นะคะที่ใช้กับเมคานิกที่เป็นbearing นะคะเกียร์นะคะที่นำไปใช้กับ high speed application ต่างๆไม่ว่าจะเป็นมอเตอร์สปอร์ตนะคะลิฟต์นะคะที่ใช้ในตึกสูงแล้วก็ต้องการที่ความเร็วสูงนะคะหรือจะเป็นพวกรถไฟฟ้าแกนหมุนต่างๆในแมชชีนนะคะที่ต้องการความเร็วสูงกว่าปกตินะคะดังนั้นนะคะหากต้องการที่จะทดสอบความสามารถในการหล่อลื่นนะคะที่ high speed condition ต่างๆนะคะ EHD high speed นะคะก็จะเป็นประโยชน์สำหรับการศึกษานะคะเพื่อศึกษาผลกระทบที่อาจจะเกิดขึ้นที่ความเร็วสูงได้ค่ะ Yes thank you
Okay, so that's all for the EHD about the film thickness, and then let's move to another area in tribology about the fatigue, which is covering the micro-pitting or pitting of the surfaces. So we will be talking about the MPR, and this will be delivered to us by Ben. So Ben, please welcome.
Thank you very much, Robert. So yeah, I'll be talking about the MPR, and the MPR is the fatigue and wear tester, which was developed at PCS to study fatigue and wear inside rolling sliding contacts. So if any listeners have any questions while I'm talking about the MPR or fatigue in general, please feel free to stop me and I can answer this question while I'm on the relevant slide. So, that being said, let's continue with the MPR. So here's the kind of main overview of the kind of features of the MPR. So it's a triple contact fatigue rig, which means that we are investigating 3 contacts in situ. We have a central roller specimen, and this is the test roller. So this is a specimen which generates the damage during the test, and we have 3 counterfaced rings equally spaced on either side. So this kind of setup allows us to test many cycles in a very short space of time. In fact, it does 1 million cycles per hour, and this allows us to test design lives, which are applicable design lives in a short space of time. So the discs and the rollers are driven separately, so we can generate slide ratios. is temperature controlled, so we can raise the temperature up to 135 degrees Celsius. And we have lubricant in the sump. So as the discs are spinning around, this lubricant is splashed around the entire chamber, ensuring that sufficient lubricant is entrained in the contacts at all time. There's a torque sensor on the roller shaft, which allows a continuous friction measurement, and we have an accelerometer mounted onto the top shaft of the disc, which gives us a monitor of the vibration, which is really useful for investigating fatigue, where vibrations are quite a large impact in the type of damage that we'll see. So I'll talk a little about the specimens that we use on the NPR. So as I said earlier, we have 3 counterface discs, and these run against the central roller, and the central roller is what generates the damage. The roller can come in multiple geometries. So we can have a chamfered roller, which gives us a line contact. So in a chamfered roller setup, we have a flat disc. This is applicable for gearing, where we predominantly see line contacts. And it's very good for generating micro-pitting damage or wear, because as the roller profile is reduced due to material loss, the pressure does not reduce as significantly. However, other contacts are used as well. So we also have crown discs. So we have a radius on the disc surface. And this gives us an elliptical contact when run against a flat roller. And this is more applicable for bearing contacts, and we can generate much higher pressures. So we can actually vary the crown radius to extremely small radii to generate high pressures such as 4 to 4.4 gigapascals, whereas the line contact will probably end up generating more like 2.5 to 3. So I'll talk a little bit about what is fatigue and why it's important in tribology systems and why we need to test for it. Fatigue is damage that accumulates due to cyclic loading. So this is often at much lower stress levels than the material's ultimate or even yield strength. And it's measured in number of cycles. This is, in a time to failure, it's measured often in millions of contact cycles. And a contact cycle is a single event. So for example, 1 rotation of a gear tooth or 1 rolling element across a raceway of a bearing. And this repeated loading of the surface causes plastic strain to accumulate. From these plastic strains, we get cracks forming and propagating, and eventually material will be ejected from the surface, and this causes pits. Because most contacts are not perfect, we have a little bit of sliding, so we have the compounding effect of sliding, which causes fatigue to be even more accelerated. So there are quite a few types of fatigue. In particular, I'm going to focus on rolling contact fatigue, which is what the NPR tests. And this is obviously most commonly observed in rolling contacts such as element bearings, gears, cams, and they're all non-conformal in nature, so they are generated under high contact pressures. So rolling contact fatigue is made especially difficult to study because it has a large number of influencing factors, such as material geometry, the geometry of the contacting bodies, pressure, the lubricant, the roughness, and of course you have sliding in the contact as well, which applies this shear force, which pulls the surfaces apart and creates the cracks and the pits that we see in bearings and gears. The 2 main types of pitting and fatigue damage we see in these contacts are pitting or macro pitting and micro pitting. So macro pitting is pitting that occurs on quite large scale. So we can see with our naked eye these large pits that form on the surface, and these are often detrimental to the application that they're formed in. So if you see, and often calls for the end of life of these components to be replaced. Micropitting, on the other hand, happens on a much smaller scale, often on the same scale as the asperities. So the asperities is the peaks of the surface roughness that are in contact, and they're measured in about tens of microns, and these can form a dense network of pits and cracks and create a continuous removal of material. And the material and the surface of micropitted surface can end up being quite dull and matte in appearance. So this is a sign. So you see the bottom here, at the bottom of the gear tooth, where it looks a bit different to the sheen marks from above. This is a sign that you've got micropitting forming, and you'll have a deviation of the profile at this point. So surface-initiated pitting forms at defects or starting like cracks at the surface and acting at local stress concentrations. So for an example of a defect would be a scratch or even micro-pitting. And then as cyclic loading continues, these cracks will propagate and go quite deep into the surface. They'll always propagate in the opposite direction to friction. And as you can see by this image this is a sectioned NPR roller here with a deep macro pit is formed. And here we have macro pitting, which is formed alongside micro pitting at the same time. And the shape of these cracks are often complex due to like material structure and steel crystal structure. So you get some branching, and this is very useful to be investigated by metallurgists or bearing companies, gear companies who are interested in looking at the steel structure and how that affects fatigue. So this crack will propagate, it will go deep into the surface, and then it may at some point return back up to the surface or interact with another crack, and you get a large chunk of material parting off and creating this large crater, this pit. Here's an example of a subsurface crack, but this hasn't formed a pit yet. This is quite interesting because you can see that the crack has actually created a different kind of crystal structure around it. So this has been etched with an acid to kind of bring out the crystal structure, and parts of the crystal structure have now actually turned white, which is different from how it would have done had the crack not been there. And this is called a white etching area. And this has been correlated to quite a few premature failures in some critical applications such as wind turbines. So there's been a lot of research into how white etching areas are formed and whether it's critical in the crack formation process. And that's what I'm going actually. So here's some examples of surface-initiated pitting. We see it often has a distinctive shape, this fan shape. The point of the fan, which is located here, this often indicates the origin of the crack, and you will see that it will have beach marks close to the origin where we have these striations where it is a stop-starting the propagation, and then towards the end of the pit it'll be a torn surface where it is propagated very quickly and the material is removed. There's also subsurface initiated pitting, so this isn't started by surface defects anymore. We're now starting at defects inside the material. These could be non-metallic inclusions. So if you etch the surface, you can really bring out this inclusion structure. Here they are here, and they look very different to the surrounding crystal, and they come up very different in the etchant. And what can happen is, after lots of over-rolling of the contact from the surface, you get cracks forming below the surface, and they will propagate in both directions. And eventually they'll come back up to the surface and they'll form this pit. And the pits look a little bit different to surface initiated pitting, but it is often quite difficult to distinguish. So, researchers will try and cut these specimens up to try and find the origin of these pits after testing. So, in an NPR, we can run a lot of these pitting tests, and the NPR is very good at running pitting tests because you can generate a lot of cycles in a short period of time. Because of the accelerometer addition on the NPR, we can monitor vibrations throughout the test. And when the test is over, we can form this pit and take it over and analyze it. We can cut the specimen up, we can take pictures, we can take and analyze the profile of the roller after the test. And here's an example of a accelerometer trace throughout the test. You can see that for much of the test, the vibrations are really low. And this is because what we're seeing is just a crack slowly propagating. But as soon as that pit is formed, you get a very large spike of vibration. And what's fantastic about the NPR is you can stop the test as soon as that pit occurs, so no more damage is accumulated after that, which means it's much simpler to analyze the results, analyze these pits that are formed from your pitting test. Next, we'll talk about micropitting. So micropitting is more of a concern in rougher contacts and thinner films where you have a lot of roughness in contact, which creates all these very high stresses very close to the surface. It occurs in these non-conformal rolling sliding contacts, quite often in gears which have a rougher surface to bearings. So you can see here in this gear, we can see where micropitting is formed, where it's duller and matter than the rest of the gear flank. And once micropitting has started, it'll spread across the whole surface, creating these large, like dense crack networks, leading to a loss of large loss of material, a continuous loss of material. And this can be akin to something like wear, but micropitting is a fatigue-driven process, unlike wear. And the debris can cause problems as well, as it can get inside the contact and actually accelerate the damage as the micropitting is formed. So the mechanism behind micropitting, it's surface fatigue. It happens very close to the surface, and it's fatigue on the asperity level. So it's caused by the surface roughness. This is mostly common in boundary or loop or the mixed lubrication regime. So at the surface roughness in contact forms these very high stresses very close to the surface, and the cracks will propagate in the opposite direction to friction. Many cracks are formed, and these cracks will interact with each other in a very complicated way, which is very hard to model. And small bits of material will be ejected continuously as the process goes. So we end up with like lots of material loss due to micropitting. And you can see here is a surface here generated on an MPR specimen, and there are many cracks and pits being formed, and it's a continuous. You'll get basically regenerate the surface over and over again, and if you could maintain the same conditions at the test as the MPR can do, you can generate a lot of damage very quickly. So here we have a few more examples of MPR testing. Now, another great thing about the MPR is you can stop the test, pause it, and you can take the roller specimen out. You can measure the level of micropitting by looking at the profile, measuring the track width, and you can see how the profile width increases throughout the test, so that we're seeing a measure of the level of micropitting throughout the test. So we have two oils here, and both oils are generating a significant amount of micropitting. The track width is here, and the track width throughout the test is increasing. So we're seeing more and more micropitting resulting in radius loss of the roller specimen throughout the test. And this can be tracked because we can take the roller off and measure it, and we can set at the end. We have a lot more micropitting at this point than this point, and we can look at the rates of material loss throughout the entire test, which is extremely useful if you're looking at micropitting applications such as gears, where you're trying to design the whole life of the gear. Yeah, like I said, we're looking at the track width, and you can slowly see it getting wider and wider and wider. So, why is the MPR useful? What industry are we interested in looking at fatigue? Well, to be honest, all industries should be very interested in looking at fatigue and wear testing. Heavy industry in particular, and transport, the energy, metallurgy. So, for example, the metallurgy, we're very interested in the crystal structure of their steels and how that is fatigue resistant. There's a lot of parameters to change there, and if you're testing steels, you want to test them quickly to get a lot of feedback. The energy sector, so wind turbines, they're seeing a lot of fatigue failures at the moment, premature failures. It's very important that they test their machine element components. The same for transport. Lubrication, so oil formulations, we want to look at how their formulations protect against fatigue and wear. It's crucial that they do fatigue testing on those too. So the MPR is all about improving the safety of machines and increasing the reliability and therefore the cost of machine element replacement. The summary, so the MPR is an accelerated rolling contact fatigue tester. It can reduce the time it takes for pitting and micropitting tests compared to other standard tests out there. It can be used for a wide variety of applications to develop new materials, looking at the coatings, the lubricants. It can mimic the parameters found in gearboxes and bearings, machine elements for a wide range of applications. And because of its free contact geometry, we can look at the real design lives for these applications. in a very, very manageable short space of time. Thank you very much.
Thank you, Ben, for that MPR, for that insight about the fatigue in the lubricated or unlubricated conditions. Next question.
ก็สำหรับตัว NPR นะคะก็เป็นเครื่องทดสอบ fatigue นะคะหรือความล้านะคะซึ่งตัวเครื่อง NPR นะคะจะมี ring roller นะคะ3 อันนะคะหรือที่เรียกว่า disc นะคะดังที่แสดงก่อนหน้าเนาะแล้วก็จะมีตัว specimen ที่ใช้ทดสอบนะคะอยู่ตรงกลางอีก1ชิ้นนะคะซึ่งเป็นชิ้นส่วนที่จะได้รับความเสียหายนะคะได้รับpressure นะคะที่เกิดขึ้นจากการทดสอบนะคะเมื่อทดสอบผ่านไปนะคะจากการสัมผัสแบบการ rolling นะคะก็คือการกลิ้งนะคะซึ่งฟาติกประเภทนี้นะคะจะพบได้บ่อยในพวกbearing นะคะเกียร์นะคะ cams นะคะก็สามารถพบการสัมผัสประเภทนี้ได้นะคะซึ่งก็จะเป็นการสัมผัสแบบ non conformal นะคะแล้วก็จะมีปัจจัยอื่นๆนะคะที่เกี่ยวข้องกับความเสียหายด้วยนะคะไม่ว่าจะเป็น material ที่ใช้นะคะรูปร่างนะคะแล้วก็ลักษณะของพื้นผิวที่สัมผัสนะคะอย่างเช่นความหยาบนะคะ contact pressure นะคะ lubricant นะคะซึ่งทั้งหมดนี้นะคะก็จะส่งผลต่อแรงเชียร์นะคะหรือ shear force นะคะที่เกิดขึ้นบนผิวสัมผัสนะคะเมื่อใช้งานไปเรื่อยๆนะคะซึ่งก็จะเกิดความล้านะคะบนวัตถุนะคะเช่นเกิดรอยร้าวนะคะรอยแคร็กนะคะจนสะสมกลายเป็นหลุมนะคะหรือว่าพอมีความเสียหายเกิดขึ้นแล้วนะคะมีร่องรอยแล้วก็จะมีการแพร่กระจายของความเสียหายที่เกิดขึ้นนะคะที่เรียกว่า pitting นะคะซึ่งก็จะบ่งบอกถึงอายุการใช้งานของวัตถุนั้นๆนะคะNPR นะคะจึงเหมาะที่จะใช้ในการทดสอบ fatigue นะคะของ surface rolling นะคะที่จะเกิด micro and macro pitting ได้นะคะเพื่อเป็นแนวทางในการที่จะพัฒนา material coating นะคะของวัสดุนั้นๆนะคะหรือว่าจะเป็น new lubricant นะคะก็สามารถทำได้เช่นเดียวกันนะคะซึ่งก็จะเหมาะกับผู้ผลิตชิ้นงานmechanical รวมไปถึงผู้ที่ผลิต material coating อีกด้วยนะคะแล้วก็ตอนนี้นะคะ MPR นะคะ approve มาตรฐานการทดสอบนะคะใน ASE International นะคะโดยทดสอบ Standard Testing ARP 6991นะคะค่ะ
Okay, thank you for that. Let's move. Is there any question from our attendees? And then you're open to raise your questions, or you can drop your questions in the chat box. And then, yeah. So if we may continue to the HFRR, so which is like most of our attendees today, they may be familiar with this rig. And then like we encourage, like if you have any specific questions or technical advanced questions, we have our expert team and to answer you about the HFR. Okay, please, Ben.
Thank you very much, Robert. So, yeah, any questions on the MPR, you just feel free to drop them in the chat and we can answer them after the presentation. So, the HFR, you know, like Robert said, most of you will probably be very familiar with this instrument. This is one of the first instruments developed by PCS. It's the high-frequency reciprocating rig, and it consists of a ball specimen, which is the upper specimen, and a disc. And this ball is loaded against the disc. And it's vibrated at a high frequency back and forth in a lubricant bath, and this simulates the performance of both fuels and lubricants under boundary conditions. The pot which holds the disc is heated and the temperature is monitored at all times, and we get a continuous friction measurement throughout the test. So here are some of the parameters of the HFR. So we can test up to loads of 10 newtons, which gives us a contact pressure of maybe 1.4 gigapascals. The frequencies are about 10 to 200 hertz, and stroke lengths of 20 microns to 2 millimeters. And with the addition of the high-powered heater option, we can go up to 400 degrees. And a benefit of the HFR is the very small amount of lubricant volume required. So it's a really good screen testing for niche applications where you're not creating a huge volume of lubricant at once. And it's the only instrument specified on the diesel fuel lubricity test methods. That's ISO 12156 or ASTM D6079. And when you have an HFR, these standards are preloaded onto the HFR, so it's very easy to test with them. But it's not just on the standards, it could be used for lots of applications too. So the HFR is a really good screening test for lubricants because we can look at the measure of friction and wear very, very quickly, and it's very easy to compare the performance of lubricants because of this. So an example of the kind of application which the HFR is very good at looking at is the piston friction in lubricant development, so sliding up and down of pistons. It can evaluate the coatings, materials, the lubricant formulation. So there's a lot of parameters that can be changed for an HFR test. And in addition, it can also look into failure modes such as fretting or false Brunelling, which is when we get vibrations in machine elements such as bearings and gears. And this can cause premature failures. So it's very useful to look at stuff like that too. Great, there we go. So here's a graph showing several tests of lubricants and the friction traces that were produced. The friction coefficient is recorded throughout the test, and we can see that it does change significantly due to wear of components. So if you get a lot of wear in your test, you can see that friction can go up, like in this specimen oil here. But other oils where you don't get as much wear, it could be quite stable. And we can see that the typical testing parameters of these tests where you're looking at friction and comparing oils would be about 3.9 newtons of load, 2.4 newtons, and a frequency of 20 to 50 hertz, so and a 1 millimeter stroke length. And we can see that there is a significant difference between all the oils, so this would be very useful for a lubricant manufacturer who's looking at developing oil formulations and want to see the level of friction and wear happening on their tests. So post-test, we can look at the level of wear as well. So the HFR specimen holder can be taken off and taken to a microscope or a white light interferometer, and we can measure the diameter of the wear scar and compare that with different oil formulation, which is very useful. And here we have two images. So we can look at the two perpendicular diameters, D1 and D2, which would define the diameter of this contact. And this could be average to get the mean diameter of the wear scar. And this is a really good quantity to quantify the level of wear which occurred throughout the test. And you can use, so this was taken with an optical microscope, but like I've said, you can use white light interferometry, which gives you a much more detailed view of the 3D data of the wear scar. And we can work out the material volume as well using simple maths to work out how much, based on the size of the wear scar, how much material was removed. So in summary, the HFR, it's on a standard for diesel lubricity, but it's also a great screening test for lubricant properties, for material, for coatings. It's very quick and easy to use, requires a very small amount of lubricant in order to set the test up. And it can be optimized to look at piston contacts, but also looking at other failure modes such as fretting and false Brunelling, which is found in gears and bearings. It takes a minimal lab space and is one of the easiest instruments really you can use for this kind of application. Thank you all.
ค่ะก็สำหรับการทดสอบหาความเสียดทานและการสึกหรออย่างง่ายนะคะ HFRR นะคะมักเป็นเครื่องทดสอบนะคะที่ใช้ในการ develop lubricant นะคะซึ่งตัวเครื่องเนี่ยจะมีบอลนะคะ on page นะคะหรือที่หลายคนนะคะรู้จักในชื่อของ upper and lower specimen นะคะซึ่งจะใช้ในการทดสอบดูการเสียดสีของชิ้นงานนะคะแบบกลับไปกลับมานะคะที่เราสามารถที่จะกำหนดสภาวะของการทดสอบได้นะคะซึ่งทดสอบได้รวดเร็วนะคะต้นทุนต่ำนะคะโดยแสดงลักษณะของการเกิด friction นะคะแล้วก็บันทึกผลตลอดเวลาที่ทำการทดสอบนะคะซึ่งจะช่วยให้ประเมินความสามารถในการหล่อลื่นของlubricant หรือ additive ได้นะคะเพื่อที่จะกำหนดสูตรนะคะหรือว่าส่วนผสมของ new lubricant ได้ด้วยเหมือนกันนะคะนอกจากนี้นะคะสำหรับ HFRR นะคะนอกจากจะทดสอบสารหล่อลื่นที่เป็น lubricant ได้แล้วนะคะยังสามารถที่จะดูประสิทธิภาพการหล่อลื่นของเชื้อเพลิงดีเซลได้อีกด้วยนะคะซึ่ง การทดสอบเนี่ยเป็นไปตามมาตรฐานการทดสอบที่ถูกกำหนดให้อยู่ในสเปคของน้ำมันดีเซลนะคะและ HFRR จาก PCS Instrument นะคะยังเป็น Source Supply นะคะของ ASTM D7688 นะคะที่บอกความสามารถในการหล่อลื่นของน้ำมันดีเซลในเครื่องยนต์ดีเซลได้ด้วยค่ะ
Okay, thank you very much. And then going further about the next topic about the high shear viscosity. So typically we have in our
this
lab
is my
viscometer, and
computer
then
diesel.
with a high shear beyond this, that will be difficult to test. And then, however, we have a current solution for that. No? So I'm calling Mr. Rory, and then to introduce this application solution for the high shear viscosity.
Okay, so yeah, another machine that we'd like to talk about is the ultra shear viscometer, the USV. And in the interest of time, I'll try to move through this quite quickly. So in real applications, lubricants often experience extremely high shear rates, which can actually have the effect of lowering viscosity, which is called shear thinning. This effect is important enough to be recognized in many standards, and being able to test viscosity under these conditions provides confidence that the oil will maintain performance over its lifetime. And it also allows optimization of the shear thinning effect, which can help find a balance between friction and wear. So to allow testing at these extreme shear rates, a precisely machined rotor is spun up to 20,000 RPM inside a stator, with a gap of just 1 micron between them. And that allows the USV to meet the specified conditions of many standards, which are listed here. And the benefit of the USV is that we can test under much more realistic conditions of shear rate and temperature. So we can test at a shear rate of up to 10 to the 7 per second, which is actually higher than the shear rate specified in many of these high temperature, high shear standards. So yeah, the shear rate can reach up to 10 to 7 per second, and some of the other specifications are shown here. So the maximum test temperature is 150 degrees. It's quite a small machine that can sit neatly on the benchtop, and it requires a very small sample of fluid, just 5 milliliters. So the plot here shows an example of shear thinning with a significant drop in viscosity between 10 to the 6 and 10 to the 7 per second shear rate. And this is the kind of thing that can be measured with the USV. And this is the sort of behavior that will be seen in a real application if it reaches shear rates of this magnitude. So looking now at the case of a crankshaft journal bearing, we can illustrate some of the effects of shear thinning. So typically the metal surfaces are separated by a thin oil film, but at high speeds this shear thinning effect can occur, which potentially can improve efficiency via a drop in viscosity. So you're wasting less energy shearing the viscous fluid, but if the viscosity drops too low, metal to metal contact can occur, and that can cause wear and energy losses. So there's actually an optimum level of shear thinning. Another important effect that can be characterized with a USV is a permanent loss of viscosity. So in this, with this effect, long fluid molecules are permanently split by the high shear rate that results in a drop of viscosity that does not recover. So this can be analyzed with the USV. It can be used to run multiple tests on the same sample in series. So here you can see that after a number of cycles, the viscosity drops and then reaches a plateau, simply as a result of intense shearing. So the USV can be used to characterize this effect in lubricants. So clearly it's very important to understand if the shear, if the loss of viscosity due to shear will happen to a lubricant in its rated lifetime, and there are many standardized tests to evaluate this. But the USV provides a very cheap alternative, and as I said, it can actually achieve higher shear rates than many of these tests. Just to summarize then, the USV is an accurate and adaptable high shear rate viscometer. It can be used to measure viscosity under realistic shear rates, meeting many standard conditions. And I can actually go to higher shear rates than the standards. So this will allow you to optimize the shear thinning effect of your lubricant, as well as being able to characterize the permanent loss of viscosity that a lubricant might experience. So I'll pause now for the translation.
Thank you ค่ะก็สำหรับUSV นะคะเป็นเครื่องหนึ่งที่ใช้สำหรับวัด viscosity แบบ high temp high shear นะคะซึ่งตามที่ PCS นะคะได้อธิบายไปข้างต้นนะคะUSV นะคะ equivalent กับ method ที่เรานิยมใช้ในการ certify product นะคะคือ high temp high shear ตาม ASTM D4683 นะคะแล้วก็ ASTM D4741 นะคะซึ่งเหมาะแก่การใช้ศึกษาลักษณะความหนืดของ lubricant นะคะเพื่อที่จะปรับความหนืดให้เหมาะสมนะคะแล้วก็มีประสิทธิภาพเมื่อใช้งานกับเครื่องยนต์นะคะเพื่อที่จะหาstability lifetime นะคะของ lubricant นะคะเมื่อใช้งานนานมากขึ้นนะคะจะทำให้ค่าความหนืดนะคะเปลี่ยนแปลงไปนะคะหรือสามารถที่จะสูญเสียความหนืดไปอย่างถาวรนะคะซึ่งเป็นอีกหนึ่งการทดสอบนะคะที่สามารถประเมินอายุการใช้งานของ lubricant นั้นๆได้นะคะนอกจากนี้นะคะบางแอปพลิเคชันนะคะที่มีการเคลื่อนที่ของเมคานิกนะคะที่เร็วนะคะทำให้เกิดเชียร์ที่สูงขึ้นนะคะและอุณหภูมิที่สูงขึ้นนะคะก็จะทำให้เกิดฟิล์มติ๊กเน็ตที่บางลงนะคะซึ่งการใช้ USV นะคะก็สามารถจะศึกษาการเปลี่ยนแปลงของ viscosity นะคะได้ด้วยค่ะ
Okay, thank you.
ค่ะก็สำหรับลูกค้านะคะท่านใดที่มีคำถามนะคะตอนนี้มะนาวไม่แน่ใจว่าแชทบ็อกซ์ใช้งานไม่ได้หรือเปล่านะคะแต่ว่าถ้าเกิดว่าลูกค้ามีคำถามนะคะสามารถที่จะพิมพ์มาใน Q&A ได้นะคะที่อยู่แถบด้านบนนะคะของตัว Microsoft Teams นะคะพิมพ์เข้ามาได้เลยนะคะ
Yeah. Okay. Yeah. So thank you. Our last part will be dealing about the empty version. This will be for the potential current between the thin film, and then the HPR as well will be delivered to us by Ben.
Thank you. So, yeah, I'm going to talk about very briefly about the HPR and the MTMEC. So these are two brand new rigs developed at PCS, and they were actually launched a month and a half ago at the STLE annual meeting. So the first one is the HPR. Now this is the next generation of friction and wear testing system. It's similar to the HFR. So it's a ball-on disc reciprocating rig, and now we have a vacuum chamber, a sealed air pressure chamber, which can run under very high pressure or vacuum. The design of this allows for the removal of the chamber to maintain the pressure or vacuum even when it's off the system, so we can test blends to be made in situ. And this is combined with the low costs of standard specimens and small sample test volumes, which are really advantageous for the HFR. So it's a reliable and cheap way to test fuels and lubricants under like different blanket environments, gases, or we can test volatile fuels and blends. We can look at the behavior of these lubricants under very low pressures, almost vacuum. We can do lubricity studies under really controlled atmospheric conditions. So what's quite popular these days is hydrogen, for example. So we could test the behavior of tribological contacts under hydrogen atmosphere. We can look at refrigerants under high pressure. So the HPR offers a wide variety and versatility of different environments that tribology contacts can now be tested under. And this can be ordered as well from PCS. The second rig I want to talk about is the MTMEC. So this is a modification to the MTM and could be bought as an entire unit or as an upgrade for existing MTM systems. And this consists of electrical potential across the contact, which is controlled using the PCS software. You can apply both a DC and AC voltage up to 60 volts, plus or minus 60 volts, and currents from 0 to 2 amps. And both the voltage and current throughout the entire test are measured in situ, so we can get an average voltage measurement of the contact throughout a timed Strybeck or traction step. But in addition, we have an oscilloscope which is connected to the MTM, and this is also integrated into the PCS software as well. So we are able to capture very high sample rates and see discharge events as they are occurring in real time. We have automatic power switching on for automatic testing, so it's very easy to set up and use for customers. And in addition, it comes with updated casings and electrical resistance switch boxes to allow a very wide variety of current voltages and powers to be tested across the contact. So this is very important for testing in EVs, where we are seeing parasitic currents being formed across contacts. Electric motors, wind turbines are also seeing this kind of damage and friction change because of electric potential across contact, and generators. So it's very topical at the moment, and PCS have risen to the challenge and developed the MTM-EC in response to customers' requests to get this into the MTM. Yeah, I'll just pause there for that to be translated. Thank you.
Thank you, Ben. Yeah.
ก็สำหรับHPR นะคะที่พูดไปก่อนหน้านี้นะคะเป็นระบบทดสอบแรงจัดทานและการสึกหรอนะคะตัวล่าสุดนะคะที่ใช้งานกับตัวอย่างที่เป็นแก๊สนะคะโดยตัวเครื่องเนี่ยจะทำการ maintain pressure นะคะภายใต้ high pressure หรือทำระบบเป็นแบบ vacuum นะคะที่เป็นระบบปิดนะคะซึ่งก็จะทดสอบแล้วก็ดูผลที่เกิดขึ้นใน specimen นะคะแล้วก็ถัดมานะคะตามสไลด์นี้นะคะตัว MTM-EC นะคะเป็นการ modify ระบบ MTM ที่มีอยู่เดิมนะคะให้สามารถที่จะวัดความต่างศักย์แล้วก็กระแสไฟฟ้าที่หน้าสัมผัสของบอลและดิสก์ได้นะคะเพื่อที่จะดูคุณสมบัติการเสียดทานนะคะภายใต้ความเร็วนะคะโหลดนะคะที่แตกต่างแล้วก็อุณหภูมิที่กำหนดนะคะเพื่อที่จะระบุลักษณะเฉพาะของลูบิแคนแล้วก็แมททีเรียลได้ค่ะ
Okay. So I think I'm calling Kun Prapason when she raised her hand. Fern.
Yes, Robert. I need to know that for MTM, we have our install base in Thailand. In case that customer need to upgrade for testing EV, I'm not sure that we can upgrade with own unit or not.
Yes, it will be question to PCS team. For the existing MTM, is there any upgrade version, upgrade kit to offer to the existing user?
Yes. All right. So this is being offered as not just a standalone kit, but you can actually buy just the upgrade version for existing MTMs already in the field. So if you have an MTM and you want the EC capabilities, you can buy the EC capabilities without having to buy a brand new MTM.
Okay. So it is upgradable. Okay, thank you very much. And then for this last part, please allow us I call our sales manager, then she can wrap up all this presentation about tribology, and then requesting the customers, and then please wait for a little time. Let's have a group photos before we officially end our event. Fern, please come in. Mike, the microphone. You are still mute. Yeah. We cannot hear your voice.
power.
โอเคค่ะ
Okay, now it's better.
โอเคค่ะ ตามที่เราสัมมนากันมาประมาณ2ชั่วโมงเต็มนะคะก่อนอื่นต้องขอบคุณนะคะทางผู้เข้าร่วมนะคะสัมมนาในวันนี้มากๆเลยนะคะวันนี้หวังเป็นอย่างยิ่งนะคะว่าทุกท่านนะคะจะได้เห็นภาพรวมของไทโปโลจีหรือการทดสอบไทโปโลจีนะคะไม่ว่าจะเป็นในการทดสอบผลที่เกิดจากการสัมผัสของผิวสัมผัสต่างๆนะคะซึ่งทั้งหมดนี้นะคะจะส่งผลต่อการออกแบบนะคะไม่ว่าจะเป็นทางด้านงานวิจัยนะคะผู้ผลิตน้ำมันหล่อลื่นหรือว่าลูบิแคนหรือกรีซที่ใช้ในการหล่อลื่นเครื่องยนต์หรือเครื่องจักรนะคะรวมถึงผู้ที่ออกแบบนะคะเครื่องจักรประเภทต่างๆนะคะแล้วก็ถ้าเกิดว่าในการทดสอบใดนะคะที่เรา provide solution ในการนำเสนอในวันนี้นะคะไม่ว่าจะเป็นทางด้าน viscosity นะคะหรือว่าการหาthickness หรือว่าtraction friction ต่างๆนะคะหรือว่าการดูร่องรอยนะคะการcrack ในบางชิ้นงานนะคะถ้าท่านใดสนใจนะคะเครื่องมือใดเพิ่มเติมนะคะสามารถติดต่อทางเซลล์นะคะให้ไปนำเสนอเพิ่มเติมได้ค่ะและวันนี้นะคะสรุปของวันนี้นะคะเดี๋ยวทางคุณโรเบิร์ตนะคะอาจจะส่งนะคะทางให้ทางลูกค้าทางอีเมลอีกทีหนึ่งนะคะและในวันนี้เองค่ะเฟิร์นรบกวนทุกท่านนะคะที่จอยเว็บมินาในวันนี้ช่วยทำแบบสอบถามนะคะเพื่อเป็นข้อมูลสำหรับพวกเรานะคะในการพัฒนาการจัดทำเว็บมินาในครั้งต่อไปค่ะเดี๋ยวขออนุญาตค้างหน้านี้ไว้สักครู่นะคะถ้าเกิดว่ามีมือถือนะคะรบกวนสแกนนะคะ QR code นะคะเพื่อเข้าไปกรอกนะคะแบบสอบถามแล้วก็กรอกเอกสารเรียบร้อยแล้วเฟิร์นขออนุญาตเปิดกล้องแล้วก็ถ่ายรูปนะคะสักครู่เดียวค่ะโอเคค่ะ
Okay. So I think we will proceed into the moment of having group photos. Thank you very much to all who attended the event today. So we look forward to see you in our future event.
Okay. Who will snap this shot, Robert?
Yeah, will take the snapshot.
Okay.
Okay.
นับไหมคะ
มะนาวนับได้เลยค่ะ
แป๊บหนึ่งนะคะ
Yeah.
โอเคค่ะเดี๋ยวเราจะเริ่มถ่ายรูปแล้วนะคะเดี๋ยวรบกวนลูกค้านะคะเปิดกล้องสักแป๊บหนึ่งนะคะเก็บภาพไว้นะคะจะถ่ายแล้วนะคะ1 2 3อีกรูปหนึ่งนะคะ1 2 3โอเคค่ะ
Yeah, thank you all. And then just in case if you want a specific presentation to your company, just email us if you need any support. Yeah. So today, thank you for your time and attending this event. And thank you to PCS for your insightful presentation.
Thank you very much for having us.
Cheers.
Thank you.
ก็สำหรับวันนี้นะคะก็ขอบคุณลูกค้าทุกท่านนะคะที่เสียสละเวลานะคะมาร่วมเวบินาร์ของเราในครั้งนี้นะคะถ้าเกิดว่าขาดตกบกพร่องประการใดนะคะก็ขออภัยมาณที่นี้ด้วยนะคะแล้วก็ลูกค้านะคะสามารถที่จะสแกน QR code ก่อนหน้านี้นะคะแล้วก็ส่งฟีดแบ็กกลับมาให้ทางพวกเราได้ทราบแล้วก็ปรับปรุงแก้ไขให้ดีขึ้นค่ะขอบคุณค่ะ
Something